This lesson is going to focus on the connections between what we've learned about the polynomial and how that helps us create graphs or write equations. So when we look at something, first we want to understand how factors are related to zeros. So recall from quadratics, if you had the factored form of the quadratic, you could take those factors and set them equal to 0 individually to find the different solutions to the quadratic. And that lets you know that on the x-axis, your graph crossed the x-axis at those points, and you could have a general sketch of the graph. Now, it's not a perfect graph, but it's a sketch of what's happening. We want to be able to do that with quadratics and more, these sketches. And so one thing we need to be able to understand is that if there is a single zero, both of these were single zeros because they would show up as solutions one time because the factor was only to the first power, that the solution just crosses through the x-axis. If we have a zero with multiplicity of 2, this would be a zero that shows up in the equation raised to the second power. That means that that solution, if you listed every solution individually, would show up twice. And that just means that though it just hits one time at that axis, it behaves differently. It behaves like a turning point, like the minimum or maximum of a quadratic function. And then extending that idea to zeros with multiplicity of 3, that means the factor would show up as cubed, meaning if you wrote every solution that you got from each factor, you would get 1 as a solution 3 times. Then it behaves like a cubic through that function and causes a point of inflection. That means it looks like it's going to be a turning point, but then it doesn't actually turn around. And so we're going to use those shapes to help us sketch. While we are sketching, when we ask you to sketch, we're not asking you to be as exact as we have with our graphing with transformations. We're not asking for exact points that build the perfect correct shape. We're asking for a graph to be a sketch, so it has to be correct in zeros, the way it behaves at the zeros, the general shape, and the end behavior. So we're going to try and sketch each of these. First, I want to write them in factored form because I want to be able to find those zeros. So the greatest common factor here is x. And then I can factor this second factor further. It's a quadratic, and you guys have methods to factor quadratics. You should be able to factor that as x plus 4 and x minus 3. From these, I get 3 zeros. I get 0, -4, and +3, each as a single zero because none of these factors had powers higher than 1 on their factor. Now, what is this graph going to look like? Well, I can tell by looking at it in standard form, it's a cubic, so I should immediately be thinking this shape. And it does have a positive lead coefficient, which means it is facing this direction where it's down on the left and up on the right. If it had a negative, that would flip. So I want to sketch that shape with those end behaviors on a graph where I know it should cross through the axis at 0, at +3, and at -4. So when I make that fit what's here, I get something like this. Now this graph is not perfect, but it is correct in the location of the zeros. The way it behaved at those zeros, it just crossed through because they were single. The general shape is a cubic, and the end behaviors are in the correct direction based on the lead coefficient. So I'm now going to do that same thing in part B. Part B is a quartic. When I see that it's a quartic, I should think something like this. Perhaps it won't curve as many times like this, depending on the behaviors. However, it has a negative lead coefficient, so I'm now going to think of those shapes yet reflected upside down. I'm going to take out the greatest common factor, which is -x². That leaves me with x² minus 25. And if I know my difference of square patterns, I'm able to figure out fairly quickly that that x² minus 25 factors as x minus 5 and x plus 5. This gives me zeros at 0, 5, and -5. And important to me is that this 0 at 0 has a multiplicity of 2. That means its behavior is going to be different than just crossing through the x-axis. It's going to behave like we saw in this visual up here, that it's going to actually act like a turning point at that 0. And that's going to be important to drawing the shape and behavior at the zeros correctly on this graph. So I'm going to mark all of the zeros at 5, -5, and at 0. And I don't know how you want to, it shouldn't be really marked differently on the graph, but you somehow want to remind yourself that at 0 you need to behave like a turning point. And now I'm going to sketch something that has these end behaviors both down towards -infinity. So my sketch is going to look something like this. This is a turning point. And that is a good sketch of this quartic polynomial. One new vocabulary word for you guys are relative minimums and maximums. So in this picture that you see here, this is a polynomial. It has a minimum but no maximum. That's generally how we've looked at them before. But now it's important to understand that all three of these points I've colored red are minimums but different kind. Only this one is the absolute minimum, but these other two are considered relative minimums. Minimums in that area, they are turning points that act like minimums. There are also no maximum for this polynomial, but there are two relative maximums. So we're just going to use that vocab in a little bit. We're going to write equations for what's here. You're going to do this on the homework, but on the homework we're not going to ask you to be specific about the a value because the graphs are a little more complicated. Now I'm going to pick out the zeros first. I see that I have a 0 at -1 and at +2, and at +2 it has a multiplicity of 2. This is going to give me factors that I expect my equation to have a factor of x plus 1 and a factor of x minus 2 raised to the second power because of that multiplicity of 2, and then I want to know if there's any sort of reflection or stretch or compression in the front. I'm going to plug in a point to find that, so I'm going to pick another random point, which in this case I'm going to pick 0, 4. And that means 4 can be the y value when 0 is the x value. This gives me 4 equals 4a, and that a is 1. So my equation here didn't need a new a value. This actually was the correct equation and representation of this polynomial. For part B, there are 3 zeros. There are zeros at -3, 0, and 4. They are all single, so those give me 3 factors. Factors at x plus 3, x minus 0, and x minus 4. We normally don't write x minus 0, we normally write that as just x. So this is probably how you would more familiar see this. And we still want to find that a value. This looks like a pretty clear point for me, and so that point is 1, -4. And so I'm going to plug those in to solve for the a value. So this gives me -4 equals -12a, which in that case, if I solve for a, I get 1/3. So then my equation would be 1/3 x times x plus 3 times x minus 4. Now, in the next portion, we're using the vocab we talked about, relative minimum and relative maximum. So you guys have estimated turning points in the previous lesson. This is just now using a more specific name. So the relative maximum here looks like 0, 4. And the relative minimum looks like 2, 0. In the other graph, the relative maximum here looks like relative max. Looks like -1.5, +4.5. And the relative minimum looks like 1.5, -4.5. And that would be it. We're going to use technology in some more difficult cases, your graphing calculator, to find those. So lastly, writing equations with verbal information. So what is a cubic polynomial function with these zeros? So remember, each of those zeros gives you a factor. And they don't give you another point it passes through or an end behavior, so that's good enough in this case, though they did say standard form. So actually we have to multiply this out. If you multiply out x minus 1 times x plus 1, you should get x squared minus 1. And then from there, you should get x cubed minus 4x squared minus x plus 4. The next one, it looks very similar, same zeros, but it has a quartic, and this 1 0 has a multiplicity of 2. So this factor of x minus 1 will now be squared because of that multiplicity. My other factors, and I don't need to put anything else in here because this does make a quartic when I have that power. Part C says to sketch. When they say the words cubic, I have this in my head. Because they don't give direction, end behavior, or the lead coefficient, you could sketch it as a reflection of a cubic as well. And we have zeros at 0, 3, as well as -3. And so if I sketch a cubic through those zeros, I could get something like this. And then lastly, it asks us to sketch a quartic, so I kind of think like this. But remember, it could have less zeros than that. And because they don't specify the lead coefficient or specific behaviors or points that it passes through, you could draw this going downward as well. So they only give us 2 zeros. Now they say this 0 at 3 has multiplicity of 3. So remember what that means as you're going to cross through it. It's going to look like you're going to turn, then you're not. We call that point of inflection. And so if I sketch this, come up to this, pretend like I'm going to turn, but then don't actually turn, and it makes that kind of like bump in the curve. And so that should relate your polynomial graphs to the equations that were written.